And we were talking about this idea of metabolism, this idea of how biological systems build molecules. And my last two chapters here, the finishing of the lipid material and then moving into polymers, kind of ties together because biology is very good at polymerizing things, and making things out of small units joined together through functional groups to make bigger systems. And we spent some time on Friday just looking at this idea to try and transition people from the detail that's necessary in organic chemistry through to the sort of huge nebulous subject of biochemistry, and for others maybe polymer chemistry and stuff like that, where the molecules just get bigger and bigger. But the chemistry is very similar, it's very much the same. And for the pharmacy medicine type people, you can see here a target. You can see here some sort of molecular target that you can intervene with a drug. And again, it's the pharmaceutical chemists who make these things and design these things, and then the biologists will test them, and if they make them all the way through to the clinic, then they can be prescribed. But this is now important in terms of structure, in terms of working out how to work out these materials, what do they look like. And this scheme here is very sort of similar to stuff you'll see again in biochemistry in the future, where it's just a bunch of names. There aren't any structures. And that can be good or it can be bad depending upon your like or dislike of organic chemistry. As an organic chemist, I want to see structures. I want to see bits and pieces that allow me to think about how that molecule is made, and then what does it do. So we talked about cholesterol a little bit. We talked about the fact that it's biosynthesized. You can build it up from small molecules. And you will see the molecules are very similar to stuff that will be on your final, things that we've been doing for a few weeks here, certainly in chapter 22. We have these simple ester-type derivatives, and if you abbreviate them as an organic chemist would, obviously the molecule here, this acetyl coenzyme A, which is this material here, this is a huge molecule, but the right-hand side of this is there for binding, so it can actually recognize a protein, and it's also there for to hold things in space. So when we think about the chemistry that's going to happen here, we have an ester, it has a leaving group attached, and we have a beta-keto ester with a leaving group attached. So we've got some common things. We can see in between those two carbonyls maybe more acidic protons. We can see the possibility of leaving groups breaking off, and simple organic chemistry to be able to knit things together. So you'll find as you transition into those bigger subjects that everything becomes an acronym or it's abbreviated, but you've got to keep in mind that these are really big organic molecules. So if we work our way through here and we talk about some of the reactions again, and then I'll transition into the polymer chemistry because this really does tie together. These types of systems here, when we take acetyl coenzyme A and condense it with acetoacetyl-CoA, you can get this type of aldol outcome. That's simply an aldol type product in which an enolate seemingly has attacked the carbonyl. You've done a nucleophilic addition and you ended up with a new carbon, a new chiral center. And that hydroxyl there is a functionality that sometimes has to be gotten rid of. And how do we get rid of hydroxyls? Well, we can eliminate, and we'll do that in a minute. So the type of chemistry that you should be thinking about for next week, obviously the second semester is all about oxygen, it's all about nitrogen, carbonyls, imines, things like that, and that is the basis of these types of systems. So thinking about what can happen here and thinking about the final, 200 points, plenty of time, but there are questions on there that are designed to make you think. Imagine that. Yeah? They're designed to make you sit there and go, huh, what's going on here? It's not just rote memorization, it's not just pure counter mechanism. It's going to be, what do I need to do here? What's he asking me? And I'll tell you now, everything on that final you should be able to do if you're passing this class. So if you just sit there and freeze and you don't answer the question, that's not a good sign. If you have a go at it and you do sensible things, and that's great, that's what we're after. We want to come out of this class ready for the upper division classes with some idea of why things are happening. So be aware of that. Now in terms of problems that people encounter, people struggle with pH. I think most of you who are passing are okay now with pH. And the idea that at high pH you have nucleophiles and negative things, and at low pH you have positive things and you have protons. And that's very important, not just for now, but for other subjects. Well, in these biochemical syntheses and in the polymer chemistry that's about to show up, we've got to be very in tune with oxidation states. So an alcohol is related to a ketone, but they're not the same. And I say this because on the last exam I got lots of people who struggled with, they took an aldehyde with excess methanol on a proton, and they wanted to make an ester. The problem is the aldehyde and the ester are completely different, right? They're completely different oxidation states. Too many people saw that as a Fischer-type reaction because they memorized it, and they didn't remember that an aldehyde plus methanol plus acid gives you an acetal. And that little thing is very telling to me, is that people are memorizing these things but not thoroughly understanding it. So I'm going to spend some time in recitation this week and on Friday when we wrap this up, hammering oxidation states so you take it with you. It's really important stuff. So in this example here, we can see a biological reduction. We can see the ester here is being lost, and we're ending up with a primary alcohol. And we can do that in the lab. You throw in lithium aluminium hydride, you can reduce that down. In this case, we're using something called NADPH, rather large molecule that delivers hydride. And I have some pictures of that in a minute. So this type of process now, as you can see here, it's the target for a pharmaceutical. The structure of this molecule, though the catalyst, the enzyme catalyst that actually modulates this reaction, has been worked out. It's been discovered. So when you see the three-dimensional structure in front of you, you can recognize, okay, the site that's doing all the chemistry has this particular shape. So I can build molecules that match that shape. And maybe they bind to that shape better than the natural ligand. And maybe you can outcompete the ligand for the drug. And then you can slow down the process. You can modify the process. So in terms of the types of chemistry, again, this is just to get you set for the final. This might not be on the final, but it's the type of stuff you should be able to look at now as a second semester finishing organic chemistry student thinking about what you should know. So in this reaction here, we've got some phosphorylations. They are simply nucleophilic acyl substitutions. I would imagine you could see that quite easily. And you put good leaving groups on there. And in this particular reaction, we put a second good leaving group on there. And this is often to work for specificity, so that in the system you might have one phosphate or two phosphates, and the system can recognize one from the other. So it's a modified little leaving group. Then we did a third phosphorylation, and we ended up with the phosphate on the tertiary alcohol and also on the primary alcohol. So now we have two different leaving groups that could undergo different types of processes. Well, we mentioned the other day that in nature, it's not very simple to make an enolate. You can't have molecules that are very basic because you're in water and they get protonated. But things have evolved to be able to get around that. And one of the systems here you can see a decarboxylative elimination. This is almost like an E2 reaction, except this carbon dioxide is serving like a proton. And of course, carbon dioxide is useful in metabolism. It can be gotten rid of. And then you see the flow of electron density onto the good leaving group. That's a very similar process to what you've seen. That's just an elimination process. And that ultimately gives us this over here, which is the IPP material that we started to use to build this cholesterol, the steroid. So with that in mind, we can go further and we think about where the building blocks come from. And I'm going to use that term a lot, building blocks. Think about retrosynthesis, think about putting things together next week. Building blocks, some simple small materials that you can either buy or in this case are available in natural sources to be able to put together to make bigger systems. And as I get into chapter 27 and talk about polymers, they get to be really big systems, millions of molecular weight. This isomerism here, everybody in the class who's passing should be able to comment on this in terms of the stability of these two alkenes. We said that the one on the right was more stable because it's a more highly substituted double bond. That's absolutely correct. In the biological system, you have an equilibrium between the two. It's an isomerase that does this, and you'll see that both are necessary. So now we have two single small pieces that you can knit together to make a bigger piece. And that will be maybe, we'll call it a dimerization. We take one and make two, we make it di, so dimerization. And as I head into 27, that becomes more apparent. The language will be fairly simple. So I have these two building blocks, and I can now start to think about how to put these things together in a pathway. And I keep referring back to this, because this is the guide. This is the whole system that's being worked out, and we're just looking at individual steps to highlight some of the chemistry that you've already seen that hopefully you take with you. So now going from this isopentenyl pyrophosphate to guranol to farnesyl is just simply adding these building blocks together, knitting them together through simple chemical reactions, not very simple biochemical reactions because they need these huge great proteins to make them work properly and make them work specifically, but it is simple organic chemistry so far. In this reaction we can see the coupling of these two materials where we have one leaving group and two leaving groups, and one of them is retained. So I would argue that everybody here should be able to work this out. It's basically this alkene down here is going after that carbon right there and booting this thing out. That would generate a carbocation. And you would prefer the tertiary carbocation over the primary, just like you would in Markovnikov chemistry. And then what you need to do is lose a proton, and you get the alkene back. So you can dimerize these things by simple addition chemistry. And as we wrap up, addition and condensation chemistry is vital. We've done lots of additions to alkenes, we've done lots of additions to carbonyls, we've done lots of condensations, right? The Fischer esterification, making amides, all that type of stuff are condensation reactions. They're absolutely essential. So with these bigger pieces in mind, we can go ahead and start doing this again, and we go from 5 to 10 to 15 very quickly, where we have farnesyl pyrophosphate. And you think about where we need to go here, we need to build a system that has more carbons than that. So we start to couple again. This reaction has exactly the same mechanism as the one previously. Carbocation chemistry followed by proton loss, and you end up with this. And FPP now is a bigger building block. And if you take my class in the spring next year, you'll learn more about this stuff in terms of its tangential uses for things like terpenes and small molecules and pharmaceuticals, in which this building block is really important, and it goes off in many different directions in different organisms to give you all kinds of different compounds. There's the scheme again. We're almost finished. This is a multi-step process with multiple enzymes that all have to sort of work in concert to be able to make this work, and of course they do. So we now go to squalene, or squalene, depending on where you're from. And this is a reaction that we haven't covered in terms of its chemistry. The actual mechanism of this is quite interesting. You'll see that again if you take that class in the spring. You take two of these starter materials, two of these farnesyl pyrophosphates, coupled together to give you squalene. And the chemistry here is quite remarkable. It actually involves cyclopropane type intermediates. It involves carbocation rearrangements. I didn't want to put it on here to frighten people, but it's kind of fun. It's a simple mechanistic problem once you break it down to its simple elements. And the idea here, thinking about looking at an exam question, looking at a problem, not just in this class but in the future, knowing that most of us will test you on stuff that you know. So that's the point, you should know it. In this case, we lose both leaving groups, so that's a problem. That means that we had to have some type of reductive coupling because we lost two oxygens. And the overall molecule here now is twice as big. You brought two of them together through a quite different mechanism to the previous one, but you now end up with this dimer. And if you started out with 15 carbons, you now have 30. Okay? You now have plenty of carbons to be able to do what you need to do. Now, all these extra methyl groups, you keep an eye on these because these are found in the natural products. They're found in cholesterol. Cholesterol has a whole bunch of methyl groups sticking off in different directions. And that will come about in a minute by a cyclization process. But what is this lacking? This thing is lacking pretty much a lot of functional groups, right? It has a bunch of double bonds, but we know for the most part that double bonds don't go after double bonds unless there's something else to initiate that or to allow that to happen. So we need some functional group on here now that's going to allow for a cyclization sequence to happen, and what we call a cyclization cascade. So this is something called squalene oxidase. It's simply an enzyme that specifically epoxidizes one end of the molecule. And it does so regioselectively and stereoselectively. Now, those words I've used an awful lot over the past 2 semesters. You absolutely must know what they mean. I'm going to ask you questions about, okay, discuss the stereochemical, discuss the regiochemical outcome. If you don't know what those words mean, it's no good. It's absolutely essential. So in this case, it is regioselective because I have 1, 2, 3, I have 6 double bonds in the starter material. And if you took that material in the laboratory and you put in some MCPBA, which does this type of reaction, it would go to all of them. Yeah? And you look at the type of double bonds that we have. This is tri-substituted, that's tri-substituted, as is that. And of course, it's a mirror image over here. So they're all tri-substituted. There's nothing different about any of those double bonds that would make one more reactive than the other. You might imagine a more substituted double bond might be more nucleophilic because those alkyl groups are pushing electrons in, but they're all the same here. So in the lab, it would be a mess. It would go everywhere. In nature, the enzyme has evolved to become specific, and it only goes at one end. And if you're making stereocenters, it'll only give you one stereocenter. It's perfect. So now we have the functional groups. The reason we need this is to enable some type of cyclization to happen. Again, electron-rich double bonds typically don't go after electron-rich double bonds, but they do go after positive things. They go after protons like we did last year, and they go after bromine, and they go after other sorts of electrophiles. So we're going to make an electrophile here to be able to get this thing to cyclize. So what we need to do is the equivalent of protonating it. And you can see now the scheme is getting a bit more complex. The pictures are getting more complicated. And when I show you this, it gets way more complicated. Okay? But this is the future for many of you. We have squalene oxide written in a different shape. This now is trying to show the fact that you do have a whole bunch of 6-membered rings possible if you make this thing knit together. And of course, epoxides can open. You know already that if you take an epoxide with a Grignard, you'll get SN2-like control, where you attack the less crowded carbon. If you attack a proton, or if you add a proton to an epoxide, it does an SN1-like reaction, where you go through the beta carbocation type species. So that seems to be happening here. If you are to add a proton, the proton comes from the enzyme. Again, this is a very abbreviated structure. ENZ is a huge, great, multi-thousand molecular weight structure that, to us in the lab, is H+. Right? I'm happy with H+. But we protonate this thing, and it starts to open up. And you can think now about looking at this. If you consider that, again, you're trained to quite a high level now in this stuff. What's happening with this epoxide opening? Is it sensible? Does it make sense? Is it a Markovnikov type process or not? Look at this starter material. Look at where the epoxide is right here, and look at where we go to down there. Is that a sensible process as far as you're concerned? Am I getting the better carbocation or getting the worse carbocation? You're getting the better one because it's tertiary. Then we have a carbocation, and you know all about carbocations now. They can rearrange, which can be a nuisance, but they're also electron poor, and they need help. So where do I get help from here? Well, if we look at the carbocation at the bottom now, we have a pi bond next door, and that pi bond is nucleophilic, and it's electron rich. This is not just random. This molecule is sat in a protein. It's being helped in terms of its stability. Its conformation is already predetermined by the shape of the protein. So the rotations around these single bonds can happen in solution, but it's all been sequestered in this pocket where everything's pre-organized to allow these things to happen. So this isn't just random. Then we get a cyclization process. You can see here the first part is the cyclization of a double bond onto a carbocation. And if you were to think about the possibilities now, if I use this to try and show, that carbon there is losing some negative charge, it's losing its electron pair, so it's becoming delta positive. In the transition state, don't forget transition states. In the transition state for that process, that carbon starts to develop positive charge. Yes, it's tertiary, but it still needs some help. And just right next door, we have another pi bond right here. So that pi bond now can start to get involved. But then you start to get delta positive build up on that tertiary carbon there. And we have another double bond. So we get this cyclization cascade, which is absolutely brilliant and sort of elegant biochemistry that we would have a really hard time doing in the lab. And finally, at the end of this, you can see now having the final cyclization to give the 5-membered ring, followed by a deprotonation. And again, this ENZ is the large three-dimensional piece, which is holding or sequestering this piece in a pocket so that all of this can happen. And one of the big differences between organic chemistry and biochemistry, as far as I'm concerned, mechanistically, is the possibility for 3 things lining up so that you can get molecule A attacking molecule B at the same time as attacking molecule C. That's very difficult to do in organic chemistry. But in biochemistry, where you have the protein there, everything's gathered together, everything's binding to the protein to stabilize it, and then these types of things can happen. So if you follow all that, what you get at the end of this is something that's starting to look like cholesterol. I can never say this word. Damaradienol. That goes on further with some functional group manipulations to give you cholesterol and a whole bunch of other different types of terpenes. And we can see now, I mentioned the methyl groups from the previous. Keep an eye on those methyl groups. Those methyl groups are all necessary in the final product. You can see here methyl groups all over the place. And some of them will be axial, some of them will be equatorial, depending upon the shape of the enzyme. But now you have a fairly, what looks like simple on paper, but very complex mechanism to show you the synthesis of that steroid. So we'll leave that there. I want to show this because I think it's frightening. This is the typical type of system that people would have to learn if you're going to medical school or pharmacy school. And it's all based on the steroid system and all the sort of interrelationships between all the different molecules. Now, the font is getting very small, and the thing is that the sequence is getting much more complex, but you're now back to this memorizing thing, which I just didn't get at all, didn't like at all. So we can see various parts of this. Once we've got, there's terpene biosynthesis, that's heading off in some other direction. We're heading off into amino acid type systems here, and all these steroids down here, all these 6-membered rings with the sort of steroid backbone that we see quite often. And these numbers, any idea what the numbers are? They're the enzymes. They're the categorized enzymes. So you can see here those numbers might need to be important in the future when you think about their actual activity. So you'll be seeing a lot of that type of thing in the future. Whatever they say about biochemistry, it's true. All of it. It's hard. So be ready for it. Now, what I want to do to wrap this up and get into the polymer stuff and then finish on Friday with a summary is think about some of the chemistry that's been happening here and put it into context with what's to come. There isn't much left. There's no new chemistry about to happen. It's just reactions you've seen used to make bigger molecules. So we've got these types of chemical reactions that can happen to put 2 pieces together. And this is very much like molecular Lego, right? If you can do Lego bricks and put those together, you can do organic chemistry. That's what I say. And we have 2 nice Lego bricks here, one of which is malonyl acyl carrier protein, and one of which is acetyl coenzyme A. They are just joined to proteins so they can be brought close to each other. And once that happens, you can get nucleophilic addition. And that type of reaction looks like an aldol reaction, but because this has a leaving group attached, you'll get a Claisen type system. That is a dimerization, if you like, because you had 2 carbons here, and you're bringing in 2 more carbons, and you end up with 4 carbons. So we might refer to this guy at the top as the monomer. Mono, 1, monomer. I'll give you those definitions for real in a second. But that now is coupling together with another 2-carbon piece to give you a 4-carbon piece. And you find in this type of system that the molecules made in nature are always multiples of 2 because of this reason. And you'll see now that if you think of the chemistry of this type of thing, it's a fairly straightforward beta unsaturated or beta keto ester. And beta keto esters are things you know about. Where's the most acidic protein on that thing? In between the 2 carbonyls. What would its pKa be approximately? Anybody pick that up? 10? Something like 10. We have a leaving group attached at one end and we have a carbonyl at the other end. And that's a fairly simple organic system if you ignore the ACP, which is a huge protein. And we have a leaving group which could be knocked out, or we have a carbonyl which could be attacked also. In this reaction, what would you do in the lab? What type of reagent would you use in the lab to do that type of process? NABH4. right? NABH4 tends to go for carbonyls of aldehydes and ketones quickly, and esters not so quickly. So you do get some selectivity. And in the laboratory, what would this be? Would it be one compound or two? Two. Racemic. The carbonyl is flat. It's prochiral. You attack from either side, you get two different molecules. In nature, you just get the one. So with that in mind, you now have a different functionality. And keep in mind that we have to get rid of some of this stuff, because I think I've said many times that you can't do chemistry without functional groups. You need the functional groups to be able to do the chemistry. You might not need them, you might not want them at the end. You might have to get rid of them, but you do need them along the way. So we can see here the sort of setup to get rid of this hydroxyl group. What would you do in the lab? Base, right? You might get that E1CB mechanism. Or acid, and get some sort of E1 process, and you could do elimination. And you'll put the pi bond here regardless because it's now conjugated. Well, you're on your way to a molecule that is completely reduced. And again, oxidation reduction will be a large part of Friday. Thinking about the chemistry you might do here, you need to bring in a hydrogen at one end, and you need to bring in a hydrogen at the other end. Any ideas in the lab? H2PT, H2PD, those types of systems. And we can actually do this the same way biology does it, by bringing in hydride. There are reducing agents that are selective for the beta carbon. You don't know those yet, but there are. And you can do this quite straightforwardly in the lab. So you've now gotten rid of the functional groups you needed to put the things together to get to that product. And if you keep going, you're going to end up with bigger systems by doing this again and again. Now, in terms of the actual steps, this is just to make sure that we're comfortable with where we are. We have this carbon dioxide behaving like a proton, and if we lose that, that's acting like an enolate, except enolates can't survive in water because they're too basic. They get protonated. And then we think about how these two molecules react to start putting 2 + 2 to give 4. What is this mechanism? What's that mechanism? Nucleophilic acyl substitution, that's all it is. You have a nucleophile being developed from this by loss of carbon dioxide. You have the alpha carbon of this molecule going after the carbonyl of that. What would we describe this as? Tetrahedral intermediate. Yes? If you're taking biochem, you're taking polymer chem in the future, stuff like that, this is really key. Very similar stuff to what you've seen. And then finally this thing collapses because it's got a leaving group attached, and we end up with a bigger piece. That's all it is a simple Kleisner reaction. Well, we can start to think about this in terms of going further and other bits and pieces. I mentioned NADPH. This is the biological equivalent of hydride. This is the same thing that we would use for sodium borohydride. It's obviously more complicated, but it's still an organic system. We can see here that the reducing agent is introducing H- by pushing electron density out of this cycle towards the hydride, which then attacks the ketone. Now, in reality, this thing is held in a three-dimensional system, so this carbonyl is the one that's being attacked, and you'll end up with a secondary alcohol in this case. Now, what's the driving force for this? Why might this be favorable? It's aromatic. Yes, it's aromatic. Just because you go from one subject to the next, the language doesn't change. P-Chem, everything changes. Yeah? But organic chemistry, biochemistry, general chemistry, it's all the same language. You just have to realize that. Well, we can do this in the opposite direction. We can oxidize by taking out hydride. You'll see that a bit later. But we now have a nice couple. And this over here, again, is very complicated. But it doesn't do anything chemically. It is the recognition unit that is on that molecule so it can bind to the right place. It's just there for recognition and binding. And once we've got all these things together, don't forget, this is all happening in the pocket of a very large enzyme molecule. You get reduction as you would in the lab. Again, look at that stereocenter down there. One only, specific. We would get a racemic mixture because we can't control that type of thing. Now, also, just to sort of get you ready for the next Monday, so there's no shock here in terms of what on earth are you trying to do to me, there's a fairly simple process. There's a beta hydroxy ester going to an alpha beta unsaturated ester. Chemically, it says at the bottom it's an E1CB. That should make some sense by now. In this reaction, we have a base from an amino acid, from a protein. Close by comes after this. Why should that proton want to come off? It's next to a carbonyl, right? It's an alpha proton. And if we have things around here, there'll be something here to help stabilize the negative charge, maybe a proton from a carboxylic acid. And then we get to this. And this is the conjugate base of that starter material, just like we've seen with our Kleisner reactions and also the Alval type reactions. This comes back down and it boots out the hydroxyl. The hydroxyl has to pick up a proton. That's very similar to what we've seen, right? If you want to lose OH, help it out. Put a proton on there, make it H2O+, and then it comes off quite easily, and that's exactly what's happened there. And so in the biochemical process, you've gone from the saturated system to the unsaturated system, doing the same type of chemistry that you've learned in 3720. In terms of other processes to finish this off, because we're trying to reduce this whole thing, the mechanism for the reduction is fairly straightforward. Again, here is a molecule that can become aromatic if it pushes electrons out with a hydride. And we get the hydride transfer to the beta carbon. Why does it make sense to go there? Why not attack this carbon? What did we learn about alpha, beta, and saturated? Why do negative things go after the beta carbon? Because it's delta positive, right? You draw resonance structures, that carbon is delta positive, which was the whole point of the Michael reaction. The 1,4 additions are all based on nucleophiles going after the beta carbon to be able to produce addition products. And then all we have to do here, we have this enolate type structure, which is probably stabilized by other things, and then it picks up a proton, and you have your product. So conjugate addition of the hydride, followed by protonation, equals H2. That's a reduction. And you end up where we need to be. Anybody want to say anything? I've promised the biochem people that you're a very quiet class. You don't say much, so keep it that way. Okay. Let's finish this off by thinking about this word polymer, by transitioning into the last chapter that I'm going to talk about. And this idea of repeatability. You now have a 4-carbon unit. The 4 carbons obviously are here. You make it 6, you make it 8, you make it 10, 12, keep going. Just keep going and keep going. And there are enzymes out there that will do this. They'll shuttle the molecule backwards and forwards to be able to add the bits and pieces. And you can see now what's happening is basically the starter material is being conjugated to the enzyme, so it can actually be dealt with now. And you can go further. There's 6, by exactly the same reaction we just saw, to give the 6th system. And you can keep going and keep going. And what we get now is a polymer, in which you have many of the same type of piece joined together to make a bigger system. In nature, you're looking at 18, 20 type of structures like that, but in polymer chemistry, you can go on for millions. So I brought this in. I'm going to do a bit of selling if people want to take my class next spring. We ended up with 25 people this semester, which was great. We might not get that many next year, but I want to try. This is the type of stuff we do in that 50, what's it called, 4891, Special Topics Organic in the spring of next year. If you haven't had organic in a while, it might be fun to get back into it because we do arrows again. It's all about mechanism, but it's applied to biological systems. And you can see at the bottom, a complicated macrocyclic antibiotic. So you can think about picking these things up if you're pre-pharmacy or pre-medicine or biology. The class is quite diverse this year. Certainly if you're a chemistry major, then this is important. This will be interesting. And what you learn along the way is targets. And you think about the processes that happen bond by bond. So if you understand that stuff, you can think about how to then maybe intervene to build a molecule that might block that process. You start thinking like a medicinal chemist. So at the start of this, to make erythromycin A, we have 2 Lego bricks, 2 building blocks, very similar to the ones we just did, except we have an extra methyl group right here. And you find that methyl group's important because there are all kinds of methyl groups sticking off this material for various reasons. So what we'll need to do is to wonder about what goes on here. That's a huge process, very complex process to give the precursor. And that's a 14-membered ring. And what we tend to forget with this class is that, okay, 5 is good, 6 is great, 3 is rubbish, 8 is okay, 9 is getting a bit iffy, 10 is but as soon as you get to 12, things start to get more stable. 12, 13, 14, 15, 16, those rings are fine. And they show up everywhere in nature. So in terms of next Monday, what's happening going from here to here? Look at those 2 molecules and tell me what the difference is. There's 1 hydroxyl been introduced, so it's an oxidation. And this is mediated by an oxidant, an oxidase. And you can see now that transfer of that hydroxyl is specific. It only goes in 1 place. You'll find that out later. And then we need to glycosylate. We need to put a carbohydrate on here. What is this functional group right here? Acetal. Yeah, acetal. Recognize those things are in great shape. That's an acetal, base stable, acid sensitive. It will break off if you put acid in there. And then we go further, we do it again, and we put the second group on there, and we finally finish this off by a bunch of different functionalities, basically ether synthesis at the bottom, and you get your pharmaceutical. But the background to it is a lot more detail. There's a huge amount of detail in terms of how that works. If you're interested in that stuff, then take that class. It's 2 semester hours, and it seems to have been quite popular. This is my favorite slide ever, because I made it myself. And it really is the interface between biology and chemistry, or biochemistry, whatever you want to call it. And this is now an attempt to show what's called a polyketide synthase, the system, the package that is used to build this beast from this stuff and this stuff, right? How do you bring all this stuff together? Well, it's very, very complex, and this protein system, it's more than one protein, has a molecular weight of over 2 million. It's horrendously big, but it does so many different jobs. And you'll find as you head in, certainly those who've got aspirations of pharmacy school, which is some of you, you'll have to get used to these types of things. Medicine, maybe. And you'll see that all these letters mean something. Acyl transferase, acyl carrier protein, forget what that was, ketosynthase, ketoreductase. These are all enzymes that do a various job, like oxidation, like reduction. And you can very simply build up polymers. There's 2 carbons, or 3. There's a bigger system, right, where you put 2 of them together. There you put 3 of them together. There you put 4 of them together, 5 of them together. And the system here requires it to go to the 7 heptaketide, and then it cyclizes. But you're starting to polymerize. You're starting to add these big building blocks together in a very simple, iterative sense to get to somewhere bigger, to get to a polymer. And my favorite from the most recent past is this one. The name of this thing is gargantulide A. It's gargantuan. Chemists have a sense of humor. Who'd have thought? And this is one of the biggest cycles that's ever been discovered. 52 members in that cycle. Now, this is very new. This is only discovered this year. So 10 years from now, if this has got any use, it turns out this compound, it's got antibiotic properties, so it kills bacteria, but it also kills you dead. So it's not a very good antibiotic in the true sense. It's never going to make it to the clinic. But somebody's going to go out there and work out how this all came together, how this was biosynthesized. And look at the relationship here. 1, 2, 3. 1, 2, 3. 1, 2, 3. Remember the systems we've talked about? 1,3-dicarbonyls have been key. Same ideas. And all this functionality now, somebody will make this in the future because it's fun to do. And then they'll start to do SAR studies. They'll start to put methyl groups on someplace. They'll reduce some double bonds. They'll get rid of some pieces and see if that has any better use as an antibiotic. But that's where these things come from. Now, that sort of summarizes what I call biology or chemistry in water. The idea of molecules needing functional groups for various purposes, particularly to do biosynthesis. And the sort of diverse nature of these things should be obvious to you now as chemists. Polymer, polar, interact with water. Polar, interact with water. Certainly, dissolve in water. No. So you have some idea of the like dissolves like idea from the lab. Take it with you. It really is key. So with that in mind, I'm done with that chapter. Anybody want to say anything? The biochemist will be happy. Last chapter I put together is 27. And I reckon I'll take 10 minutes today and then most of Wednesday and be done with this, and then Friday we'll talk about wrapping up and transitioning. Polymers are one of the most important type of compounds in industry. Most of the things that you deal with. This is a polymer. This pen is built of a polymer. The seats you're sitting on probably are built of polymers. And certainly the engineers should be interested in this stuff because a lot of you will end up in this industry. You will be able to see here all sorts of applications of everyday, what seem to be mundane molecules, but the chemistry behind them is fairly fascinating and simple. And as you start to see the bigger picture in chemistry and biology and other systems, you notice that things are the same. They repeat. So starch is a polymer. We metabolize starch to release energy. Amino acids put together to make proteins, they are polymers. Plastics are polymers. You can see here various examples of different systems. You can see at the top left, the worst one of the lot as far as many people are concerned, polystyrene or styrofoam. Now when I first came to this country, every single fast food restaurant served you whatever the food was in one of these styrofoam boxes. Anybody old enough to remember the clamshell things? Given our age away, aren't we? Yeah. But you throw those things away, which people tend to do. You know, you drive down the highway, oh, I'm done with my dinner, out the roof, out the door. Those things will last forever. Those things do not break down in the environment. There are no enzymes out there or bacteria that will break down that plastic. So we ended up with this huge mess of polystyrene or styrofoam. Now the thing with this stuff is it's so light. Yeah, you get something from Amazon, often it's packed in one of these things. Yeah, you got styrofoam there because it's so soft and it's so light. but it's a nuisance because you think about, the old argument that people use to trick high school kids. What's heavier, a pound of feathers or a pound of lead? And Billy Bob's sitting there going, oh crap, I hate math. What's heavier, a pound of feathers or a pound of lead? They're both the same, right? And what you think about is density and things like that. A pound of lead might be that much, but a pound of feathers will be a big box. This stuff is incredibly light in terms of its density. And if you throw this in the ocean, where does it go? It floats, right? It floats. And there's some statistic out there that says there's billions of tons of this stuff floating in the ocean, which is kind of sad because it isn't going to go anywhere. So one of the big deals these days is to build polymers that will go someplace once you're done with them. And you've noticed in the past 10 or 15 years, recycling has become a big deal. When I was a kid, no, I just threw everything out. Landfills. But then you start to worry, especially when you live on an island. There's no more land. You can't fill it, right? So people start to get a bit more interested in this stuff. And then when it becomes economically viable, people get very interested in this stuff. So now people are developing bioplastics. And down in Pittsburgh, some of you will end up, I imagine, here, Bayer are very big into this, the idea of bioplastics, using biological building blocks to build plastics. Because then at the end of the day, you've got pieces in there that an organism might recognize, a bacteria might recognize. You might be able to then have this thing be decomposed by some bacterium or some sort of microorganism, which can then regurgitate or reproduce your monomers, and you can go back and do it again. So lots of simple ideas that are starting to take hold. Here we have biological polymer, protein. Talked a little bit about those. You'll see those a lot in the future. But again, it's amino acids, A, B, C, D, E, F, G. Just keep adding them in chains, and you get polymers. Down at the bottom, starch. We can see now with the glucose units, we have enzymes in here that will break these pieces down. I think a big problem in the future will be, my pet hate is cutting the grass. I hate cutting the grass. And where do all those grass clippings go? If you do it often enough, you can keep it low. But if you have to do it after about 2 weeks or 3 weeks, and you have to throw that grass out, it goes someplace. All that grass contains organic starter materials that could be used for other things. So you imagine how many people cut their grass and how often they do it. I must do it about 25, 30 times a year. Hate it. But all that material is organic material that's going to waste. So one of you has to invent some system that will then take that material and break it down into useful stuff that you could sell. And then it becomes useful. Other things, obviously not related to grass here, but plastics. Anybody who's got a plastic drinking bottle made out of polymers. Different types of polymers, different functional groups that give you different properties. So what I've got here is a bunch of slides between now and Wednesday to look at the basics of this, to give you some definitions that I think you should take with you, and some idea of how big of a subject this is. Some of you will definitely end up in this industry, so it's important. This part of the world happens to be world famous for polymers. The University of Akron has its own college of polymer science and engineering. Right? That's just a college. It's a huge endeavor. And they are world renowned. They've attracted a lot of very good people, lots of money, and they build all sorts of stuff from plastics all the way through to synthetic skin and stuff like that. Okay, trying to mimic skin so you can do skin grafts. If anybody's interested in that, let me know, because they really are good if you're interested in going there. We have, on the other side of the border, for those of you who are from Pennsylvania, Carnegie Mellon is also world class. When we say world class, I mean we're like top 5 in the world for polymers. And Krzysztof Matuszewski has basically blown this subject wide open. He's probably in line for a Nobel Prize. If he doesn't win a Nobel Prize, we'd be very surprised. And his ideas of how to build off of polymers, how to build polymers and then make them build themselves, self-replication, stuff like that, is genius stuff. And that's stuff that can be commercialized. These guys have patents. They publish and they have patents, and they have lots of clever ideas that eventually will make it into industry. Now, anybody recognize these? I would hope so. Right? Dr. Jenner, who's our 3rd organic chemist, you remember from last semester, he hasn't won a Nobel Prize yet, but he's on his way. His interest is in metal organic frameworks, which are polymers in their own right, in which you have a metal in the middle and you build off of it with organic pieces. And then you keep adding those pieces bit by bit by bit. And you make these huge, great structures. If you're interested in that type of stuff, go talk to him, because he's always looking for students. And you should be thinking about research in the future at some point. Well, these types of structures now have lots of potential for things like gas sequestration. So think about carbon dioxide in the atmosphere. How do we get rid of carbon dioxide in the atmosphere? If you could trap it in something, then you can seal it. You can take it out of the atmosphere. And these types of things all have polymeric. You see the long chains where they all repeat? they have gaps in the middle or voids, and those voids can be designed to have different sizes. And if that's the case, you can trap different molecules, you can separate hydrogen from oxygen and stuff like that, and very useful in terms of industry. So talk to him if you're interested in that stuff. Now, this is the best I could find this morning as I was trying to think about what to say here. This is a depiction of a polymer. It is a long, 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 long chain. They're not infinitely long because eventually the chain stops for some reason. But you can add one molecule to 2 to 3 to 4 to 5 to 6. And you can keep going many, many, many different times to make these long chains. And you think about the properties now of these molecules. If you start adding small carbon piece to small carbon piece, and it's alkane, then it's very nonpolar. It's not going to dissolve in water. If you have functional groups around here, such as hydroxyl groups on a carbohydrate, those come with the polymerization, and they make the polymer soluble. So you can tune how soluble your materials are simply by deciding what functional groups to start with. In terms of analysis of this stuff, this is just a bit of a sell for research in the future. We happen to be very well equipped for this stuff, certainly in the chemistry and engineering departments, chemical engineering and mechanical engineering. We have all sorts of spectroscopic tools that you can use. Some of you have already done this. We have the basic NMR spectrometer on the right that some of you already used. That's a nice instrument to be able to see polymer structures. But then we get into these bigger molecules, and they don't dissolve up in our solvents, and we have trouble seeing them, so we need other techniques. X-ray diffraction, some of you might have already done this or seen it. At the very least, you might come and have a tour and see what we've got there. But you can get crystal structures very, very quickly. Those structures here, some of those are crystal structures. You can see the actual arrangement of atoms in space very quickly. Then at the bottom, we've got the one of the SEM, scanning electron microscopy. I think we have 4 of these things now, all designed to look at polymer-type materials or materials that have big structures. And you can see here from the University of Washington a picture of a polymer. And this polymer, to me, is starting to look biological. You think about wound healing. You think about how the body recruits fibrinogen and whatever it is, and all these platelets and stuff, to a place that's been wounded. And it starts to build this fibrous network to seal the wound and then eventually to replace with good skin. This is very similar to that. It's what they're doing. They're trying to mimic nature by developing biological polymers that recruit and find their way to a certain place and then could be used as a matrix or a lattice to be able to build off from. So those types of biological engineering, biomedical engineering, will be big, big deal in the future. So you can do those sorts of things here. That's the point. Here's my little cartoon of what polymerization entails. You take something called a monomer. I have these definitions coming up in a second. We'll see them all in a second. We have a monomer. It's usually a simple small molecule. It might be a benzene derivative. And you have some functional groups attached to it which can then react with other pieces. But they can react with themselves. Molecule A reacts with molecule A. And you can make a dimer. And that dimer still has functional groups attached. And that can come together with another molecule and make a trimer. And you can keep going and keep going and keep going until you get to the bottom. And the bottom is something I think you should be familiar with. Put an asterisk next to this. This is the universal way of communicating a polymeric structure. You look at the molecule and you try to pick out the simplest repeating unit. I'll say that again. When you look at the polymer chain, you try to pick out the simplest repeating unit. So that might be a benzene ring with some functional group attached, maybe an ester. I'll point some out as we work our way through here. But these things go on indefinitely until something happens to stop it. Now that stopping could be a termination step in a radical process. It could be the fact that you're in solution and all of a sudden you got to a point where it doesn't dissolve anymore, so it precipitates. And if it precipitates, it's done. Yeah, the equilibrium gets pushed to that product. So polymerization now, I see these square brackets at the bottom. This is the universal way of describing a polymer. And the N here is simply the number of repeating units. And this could go up to millions, depending upon the conditions that you're using. So as we work our way through these last 50 or so slides, keep an eye on that. Polymers are huge, but they're represented by a very simple, small structure. It can be easy to get lost there. So I have some definitions. It would be good if you can remember these things, not just from my class, but to sound informed later on. When you get to biochemistry, which is a slightly different language, when you go back to biology, which is a slightly different language, it's all polymer chemistry. So the monomer here is from the Greek one, mono, and I guess meros means part, so one small part is a monomer. And you've seen these things before. If you go to Home Depot or to Lowe's and buy some glue, some epoxy, you get the two pieces and you mix them together and you're doing a polymerization reaction. You're taking two monomers and making them polymerize. We can see here oligomer. You should have heard that word by now, certainly if you've taken any biology classes. So the oligomer is a few of these things put together. Maybe a added to itself 5, 6, 7, 8, 9, 10 times. Yeah? It goes up to 100 here. So a ligament could be a DNA fragment with 75, 80 different bases in there. So those types of ideas span the different subjects. Polymer, again from Greek, poly meaning many, as it does in any other language, any other type of words that you can think of. And these are now getting to be big. These are now getting to be millions and millions of molecular weight. So those are the basic three definitions. How do we make them? That's what we'll do Wednesday. Addition polymers. You add things together. Where does addition chemistry come from? What do we add? We did additions to alkenes. That's a big deal here. You can do additions to ketones. Maybe not so important here, but you can polymerize like that. So addition polymers mean exactly what they say, using the addition reactions that you've seen over the past year. Condensation polymers, esters, polyesters, amides, polyamides, nylon, stuff like that. Very simple ideas again. And this will be a condensation reaction in which a small molecule is lost from coupling two pieces together to make that bigger system. And copolymer, maybe not so important just now, but you might see this in the future. You might be able to mix a couple of different starting materials. Maybe you have A and B, and they both have the requirements for polymerization. And you mix these together, and all of a sudden you get polymers that have AB, 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 AB structures, or AAB, AAB. And you can come up with different structures like that. We're starting to do a little bit of that in my lab. The word I want to emphasize today to get this started is tacticity. And this is a big deal in terms of economics. Being able to make compounds that are reliable and have similar structures. So this means arrangement or order. And I'm just going to show you 3 pictures and then stop for today. In terms, and I'm going to come back on this. This is what tacticity means. If you're lucky enough to develop a synthesis in which all of your R groups are on the same side of the polymer, you have a pure polymer, right? You have a homogeneous polymer in which everything is predictable. Why does that make a difference? Well, if you're packing these molecules together and it's all uniform, maybe they'll pack together tighter. Maybe it'll crystallize instead of being some gum or something like that. So this is the isotactic where everything's on the same side. We have syndiotactic where everything is random. Well, actually, this isn't random. This is opposite. Front, back, front, back, front, back. You can do these things now. You can make these compounds this way. And the other one is atactic, in which there's no order. It's just completely random. And this is a big deal because of the structures of the bigger system. When these things start to pack together, if they're random like this, maybe they don't become a crystal. Maybe that's a big deal if you're trying to make something like a plastic bottle, things like that. Now I'm going to stop there. I'm going to carry on with that on Wednesday. In recitation this week, we are summarizing